Welcome to screencast session. So another application using that breadth first searches, longest path of direct acyclic graph. So it's a very interesting application. So whenever you have that dependency of vertices, so what time it is going to be processed. These scenarios can be used this application can be used whenever you have that sequence of courses. There is a prerequisite courses, there is independent courses. So how much time to finish up all these courses to complete a program. So similar way, how much time to finish up that all of the tasks to complete a project. Some tasks are dependent, some tasks are independent. So what is the maximum time to take complete that all of these particular tasks. So let's go for the implementation. For this implementation, we are using same pre-implemented or existing implementation of the queue. So let's implement that longest path. It's almost similar to your topological sort with little modifications. So let's have that. So here also that in degree, there is a longest path which you are maintaining as two different dictionaries. Both of them are empty dictionaries. So then we are trying to do that. So that particular in degrees values we want to put it that 0, and as well as the longest path values we want to put it the 0. For that we want to use it each vertex inside your adjacency list, the keys we are getting. So we are updating the two dictionaries with initial setup of values. So that's in degree of that u we are updating, and as well as that. So the longest path of that each particular u we are updating with 0 and 0. So we have been initialized. So later we want to update the in degree values, because based on the adjacency list the in degree values has to be updated. For that we use it, nested loops, the u in that adjacency list of keys. So each key what you are getting, whatever adjacents are there, that adjacents we are retrieving into the v. So inside your adjacency list, so that particular u, what adjacents belongs to that u. So in that the in degree we are evaluating the in degree of this v is existing value plus 1. So generally existing value is 0, because already we did it that initialization in the 28 and 29 line number. So let's go for that instance of the queue we are creating, and then we are adding that 0 in degrees to the queue. So let's create 0 degree things which are into the queue. So we want to create a 0 degree. So queue we are creating. So it is instance of the queue existing class, and we want to add them into the queue for each vertex in your adjacency list of these keys. So wherever that 0 in degree is there, we want to put it into that queue. So let's do that. If this particular in degree is 0, we want to add it into the queue, 0 in degree queue. So 0 degree queue, we are adding that NQ of the particular vertex, so which is there, that is U. So we have been added 0 in degree, and now the queue is having 0 in degree. Let's do that traversing. So until my queue will become empty. Until my queue will become empty means until my particular all of the 0 vertices, 0 in degree vertices are visited. That is not 0 degree queue is empty. So until it is not empty, we want to repeat it. So inside of it, we are getting the current vertex. So let's do that current vertex. We are getting from the queue itself. So that is, we want to get it. The 0 in degree getting is already we have the DQ operation. Whatever the first 0 in degree is there, that we are getting. That in degree of this current vertex, we are decreasing by -1. So we do that -1. So then we want to do a nested loop, whatever adjacents are there for this 0 in degree. So for that we want to use it, adjacent vertex loop, which are adjacent to current vertex. So that in degree of, so adjacency list of the current vertex, who are the adjacents are there. So that adjacent, each adjacent we are getting into adjacency vertex. So let's do that updating of this adjacency vertex. The adjacency vertex In degree also we are decreasing, that's to the -1. Now the interesting path of the longest path we want to get it. So how could you that longest path is? The longest path of this adjacency vertex is very simple. Whether that existing longest path is higher or new one is higher. So by default it is having 0. Definitely the new calculated one, the longest path of existing adjacent vertex is better value, which is a bigger value, or the longest path of that current vertex plus 1. So definitely whatever that plus 1 is there, that's going to be bigger, because first time everyone is having the longest path is 0. So maximum value we are getting. So once after done, if your in degree of this adjacency vertex is 0, again we are adding that particular adjacent vertex to that 0 degree queue. So we have already 0 degree queue is there. Into that we are adding adjacency vertex. So the adjacent vertex is there. So that we are adding. So it is a function. Okay. So that's added. So once added, we got it the same repeating of the loop from the 43 line number. This part is repeated until all of my vertices are processed. So this is updating comment. Actually it has to give it, the maximum degrees updated. Whatever the longest path is there, that is updated. And this part is exclusively we have done it using the if condition, because adjacent vertex, if it is reached to 0, simply we are adding into the 0 degree queue. So finally we got that longest path result only we wanted. So the longest path result is available with a dictionary. So the dictionary is lpath. So that return lpath value. So it is done. The function is, let's implement the main function. So the main function, we are taking a graph with adjacency list of dictionary. It contains that 0th vertex. It has the adjacents of 2, 3, 4. Generally I take the same kind of graphs which I use it for topological sort, because it is almost similar to the topological sort only. So then first vertex is having 2 adjacents of 2 and 7. And second vertex is having 2 adjacent, it could be 1 adjacent of 5. Third vertex is having 2 adjacents of 5 and 7. And then we are going the fourth vertex, it's having only 1 adjacent, I want to make it 7. And fifth vertex, I want to make it 6, 1 adjacent. And as usual, that is 6th vertex, we want to make it 7. And let's have the last vertex 7, it's not having any adjacents. So we have done that adjacency list. Let's call that above function, that is the longest path, the result of the longest path I wanted. So that's the longest path list of that adjacency list. So let's call this. So we want to see that how much time to require that all of the 7 vertices, 0th time, first time, second time, in that way. So let's run this. Yes. So during the 0th time, the 0th vertex is processed, first vertex is processed, because the 0 is not adjacent to anybody. 0 is having some adjacents. Similar way, 1 is not adjacent to any of the prior nodes. So 1 is having 2 adjacents of 2 and 7. 1, 0 and 1 is finished at the same time of 0th time. At first, the unit of 1 first time, the second vertex and third vertex and fourth vertex are finished, because all these 2, 3, 4 are concurrently can be processed at time 1. Similar lines, fifth vertex is processed, or fifth job is processed during the time of 2. Sixth vertex is processed during the time of the 3. So simply it is 6th job. It can be finished at the time of 3. And the last job it is finished is 7th job. So what does it mean? That, to complete all of these jobs, you require that maximum time or maximum length of 5, because 0 to 4, if you consider, it is 5. Similar lines, to complete all of the courses in the BS program, maybe you require that 5 terms, something like, you can assume it, because some prerequisite courses, some post-requisite courses, so not post-requisite, sorry, it's a co-requisite. So co-requisite is a concurrent one, what you can say is. So this is the fantastic application. So using direct acyclic graph and BFS procedure. So we have done. So longest path calculation. Hope you understand. Thank you very much. Have a nice day.